In this video, we are going to solve problems related to statically determinate trusses. For our first problem, we have to determine the force in each member of the truss and determine whether they are in tension or compression, assuming all members are been connected. Before we begin determining the forces in the members, we need to determine the external reaction forces at the roller and the pin connection. We can do this either taking the moment at pin connection B or at the roller A. I'm going to take moment about the point A. We have counterclockwise Gx, and it's 3 meters away from the roller. Then we have 3 external forces acting at joint BCD with the same intensity, and first reaction force is 2 meters away, second at 4, and last one at 6, all equals to 0. Solving for Gx, we get our solution as 20 kilonewton, and this gives us our x-axis for pin connection G. Now we can sum the forces in x direction in order to find a reaction value for horizontal reaction at A. This is going to be Fa, take away Gx, which is 20 kilonewtons, all equals to 0 because there isn't any other external horizontal reaction on this truss. Solving for Fa, we get our solution as 20 kilonewton. Finally, we can sum the forces in y direction using our vertical equilibrium equation to get our value for vertical reaction at G. This is going to be positive Gy, negative 3 times 5, which is 15, all equals to 0. And solving for Gy, we get our solution as 15 kilonewton. Now we can start solving for individual members. Because we need to find force in every member of this truss, we're going to use method of joints to solve this problem. Let's draw the free body diagram for joint D. At D we have one external reaction of 5 kilonewton, and then we have reaction from member CD, and we have another reaction vector for member ED. Using the Pythagoras theorem, we can find the length of this member FD, and this is going to be square root of 3 squared plus 4 squared, which is going to be square root of 25, which is simply 5. Now we can sum the forces in y direction in order to find our value for force in member FED. So it's going to be force FED in positive direction times three over 5, and then take away 5 kilonewton, all equals to 0. Solving for force in member FED, we get our solution as 8.33 kilonewton, and this member is in tension. Now we can sum the forces in x direction in order to find the value for force in member CD. Force FED we just found, and it's 8.33 kilonewton. And because we want the horizontal component of force FED, it's going to be 4 over 5. Take away force CD, all equals to 0. Solving for force CD, we get our solution as 6.67 kilonewton, and this member is also in tension. Pardon me, I missed a sign here. Because our force FED, or at least the horizontal component of force FED, is going in the negative direction, so it's going to be negative. And this will result in our force CD is negative as well. And that means we assumed our vector to be in the wrong direction. Therefore, this vector is going to be in left to right direction, or pushing at the pin. This means this member is at compression. Now that we have found the forces for member CD and member FED, we can proceed to the next section, which is going to be our joint C. At joint C, we have external force of 5 kilonewton, force from member CD at 6.67 kilonewton, unknown force in member CE, and another unknown in member BC. Let's sum the forces in X direction to find the force in member BC. It's going to be force BC plus, or negative in this case, because this member CD is in tension, 6.67 kilonewton equals to 0. And our force BC is simply going to be 6.67 kilonewton, and this member is in compression as well. Now let's sum the forces in y direction. And we're going to have force CE as 5 kilonewton, and it's going to be in tension. Now we can start drawing our joint E. At joint B, we have force fraction at CE is known, it's 5 kilonewton, and another unknown from member BE. We are going to tilt our x and y axis by 36.87 degrees in order to avoid simultaneous solutions. To find the horizontal component for force member BE, first of all, we would need to determine this angle from the y-axis. In order to determine this, first of all, we need to determine our angle BEC. There are many ways to determine this angle. What I'm going to do is going to find the length of member EC and use that value to determine our angle beta here. We already know our angle for angle CDE, and if we take tan 36.87 degrees times 2 meters, and we should get our length for member EC. Solving for EC, we get our length for EC as 1.5 meters. We can use our newly found length of EC using tan to get our angle BEC. Our angle beta is 53.13 degrees. This means since we have tilted our x and y axis by 36.87 degrees, our angle between the new y axis and the vector is 16.26 degrees. And since we are looking for our vertical component for B in this equilibrium equation, so it's going to be cos 16.26 degrees. And then the vertical component of external force reaction, 5 kilonewton, which is going to be negative as well, 5 times cos 36.87 degrees, all equals to 0. Solving for force BE, we get our solution as 4.17 kilonewton. And because we got our solution in negative, this means we zoomed our vector in the wrong direction, and it should be facing the joint E. And this means this member is in compression. Now we can sum the forces in extraction in order to find the value for force in member Fe, which is simply going to be negative force Fe plus 8.33. Then we're going to have positive horizontal component of Pe, which is simply sine 16.26 degrees times our newly discovered value for force Be, which is 4.17. And then the horizontal component of our external force reaction, all equals to 0. We get our solution for Fe as 12.5 kilonewton. And this member is in tension. Now we have found two more members. Now we can proceed to joint B. Joint B will help us determine the value for member AB and FB. To solve for member AB, let's sum the forces in extraction. So we have negative from member BC, 6.67 kilonewtons. Horizontal component of member BE is going to be negative 4.17 2 divided by the hypotenuse or the length of member B, which is simply using the Pythagoras theorem, is going to be 2 squared plus 1.5 squared. All of these are square rooted. And then finally plus force in member AB, all equals to 0. Solving this equation, we get our solution as positive 10 kilonewton. And this member is in compression. Now we can sum the forces in vertical direction in order to find the value for member FB, which is simply negative external force of 5 kilonewton plus force in member FB and the vertical component of member BE, all equals to 0. From this equation, we get our solution as negative 5.43 kilonewton. This means we assumed our vector in the wrong direction. Now we can sum the forces in y direction in order to find the value for member. Now we can sum the forces in y direction in order to find the value for force in member FB. It's going to be positive member force FB, negative external reaction, and vertical component of force PE. All equals to 0. Solving for force FB, we get our solution as positive 7.5 kilonewton. And this member is in tension because our vector is pointing outwards from the pin connection. Now we can go to our joint F and draw its free body diagram. Here we have two unknowns, force Fg and force Ef. We can sum the forces in y direction in order to find our solution for force Ef. So our force Ef is going to be, first of all, we need the vertical component of force Ef, which is simply going to be 3 over root 13 negative 7.5 plus the vertical component of member EF, negative force FE times three over root 13, all equals to 0. We can sum the force in y direction in order to find the force for member EF, which is simply going to be positive force EF, and the vertical component, in order to find its vertical component, is simply going to be 3 over root 13, then negative external, or sorry, the force of the member FB, 7.5, and take away horizontal component of member EF, all equals to 0. Solving for EF, we get our solution as 18.03 kilonewton positive. This means this member is in compression. Now we can sum the forces in x direction in order to find the values for member Fg. We can have positive member Fg force, horizontal component of member EF, and the horizontal component of member EF. Solving for member GF, we get a solution as 20 kilonewtons, and this member is in tension. The only remaining member left is now is GA. To solve for GA, we can draw the free body diagram of the member G, or the joint G, and this simply going to be unknown force of member GA, recently found force of member FG, which is 20 kilonewton, fractions of the pin, and looking at this joint, we can easily determine that since there isn't any diagonal force, it is simply going to be 15 kilonewtons and in tension. This solves our solution.